Alrighty, hello all, and welcome to 2.3 and 2.4 review. So basically the point of this before I start is going to be, here, let me turn on my mouse thing real quick. We're going to be going over the atomic structure of atoms, just a basic thing on that, and then atomic weights. So to get started off, let's go over 2.3. So some things that are going to be notable in this chapter are the charge of protons, which are equal to that, which is 1 coulomb. So this makes it easier for us to do charge of an electron, which is 1 and plus, well, negative 1. And the charge of a proton is plus 1, since they're oppositely charged. So also things that you'll find in atoms are neutrons. They don't have any charge at all, so the only thing they matter for is weight. So atoms are going to be measured most of the time in angstroms, which is very small, I might add. So 1 angstrom is equivalent to this. So very small, 100 picometers. Just a quick thing, a little quick diagram, a little quick word problem if you want to do it real quick. If you want to do it, pause your screen or pause the video, do it real quick, and then I'm going to show the answer in a second. Alrighty. If it would load, there we go. There's your answer for you. Alrighty, so here we go. So since protons are plus signs and they're equal to plus 1, and electrons are equal to minus 1, and each atom has evenly balanced pluses and minuses. So let's just do these problems right here real quick. So A, if an atom has 15 protons, how many electrons does it have? So these I'm going to walk you through. So since an atom has 15 protons, that means it has a positive charge of 15. So to balance that out, we need a negative charge of 15. So therefore, we have 15 electrons. And then the protons. The protons reside in the center of the atom. All the particles in an atom that carry weight or have weight are going to be found in the center of the atom. This is the proton and the neutrons. So, next thing. Atoms themselves have very small masses. I'm not completely reading from the text, but also it's a good point. They're very small. You're going to be measuring a lot of very small masses. So most of the time in chemistry, when you're dealing with elements, you're going to be measuring things in AMU. So 1 AMU is equivalent to this many grams. So really, really small. Anyways, so here is the masses of protons, neutrons, and electrons. So you can kind of see from this that that didn't work. Go away. There we go. That protons and neutrons weigh approximately 1. There's a few digits on the back here, but relatively equal. They can both be rounded to 1. And electrons are almost negligible compared to them. So, where's my next thing? I believe it is in this next part. I apologize for the load times. My Chromebook is not speed. There we go. Alrighty, so. Where are we? Alright, so. Our next thing. The way they write mass numbers and symbols. So, this is going to be your diagram that you're going to use for the next few problems right here. So, you have your symbol element, which is going to be your one letter that you find in the periodic table. So, it'd be H for hydrogen, P for phosphorus, which was another one, Ag for silver, going to be all right here. So your mass number, this is going to be the one up top. It's going to be your number of neutrons. This is going to be your number of neutral particles within the atom. These are all going to be found in the center of the atom. And remember, these do not add and affect charge in any way. They only affect weight. This is how you can get isotopes, because this number can change. Next thing is going to be your protons. This is your positively charged particles found in the center of your atom. So, for example, carbon. Before I actually get to that, every single atom is defined by the number of protons it has. You can never add or subtract protons. You can only add or subtract neutrons to make an isotope or electrons to make the atom charged differently. So, protons never change. So, for example, oxygen, it's always going to be 8. Carbon, always going to be 6. Gallium, always going to be 31 protons. Magnesium, always going to be 12. No matter what, you're always going to have 12 protons. So this number right here is going to be affected by the symbol. So let's just say if we change this to magnesium real quick. So the one I was talking about, this would be Mg. This number is 12, and it always will be 12 from any magnesium isotope of any type. Alrighty, so for example, here's a little bit of our isotopes right here. So carbon, so that number is down here. It's missing, but you don't truly need it because it's going to be 6. You know it's going to be 6 when you see carbon. So from this symbol, you can tell that the number of protons is 6. It's always going to be 6. Remember, we're only working with carbon here. So protons is always never going to change for the same atom. So carbon, going to be 6. Fill out that column. Number of electrons. Since we're working with evenly balanced atoms here, these are all going to be 6, since the number of protons has to equal the number of neutrons. What they left out up here is there's normally a number up here is if you have a positive negatively charged atom. So that's if you're missing or gaining electrons. That is going to be in a later chapter. You don't have to worry about that yet. But, so right now, since we're working on just this, keep this number 6. This number is equal to the number of protons that you have. Next, number of neutrons. So when we talk about carbon, this is going to be your overall weight right here in AMU per se, but rounded AMU. So since you have 6 protons and you need an AMU of 11, you can kind of do simple subtraction. So 11 minus 6, that gives you 5 neutrons. Or let's go down here a little bit. So you have 13. You have an overall mass of 13 AMU. You have 6 protons. So you do 13 minus 6, that gives you 7 neutrons. And that's how you can kind of do that from those symbols. Ooh, we weren't supposed to do that. All right, so let's do these real quick. Say pause your screen, do those, and see what you can come up with numbers. Alrighty, welcome back. So here's going to be your solutions. So as we talked about before, we're going to be working with gold. So first we go to our periodic table and find gold. Gold is 79. So that means that gold is going to have 79 protons. Since we're working with no charged atoms right now, gold is also going to have 79 electrons. So you can no longer have to worry about that. Since the overall mass of this atom is 197 AMU, you can go in here, right here, see it, what we're going to do. There we go. 197 minus 79 equals 118 neutrons. Same process with strontium right here. The atomic number of strontium is 38, so you take the 90 from the isotope, minus 38, 52. Alrighty, so here are some problems. If you want to pause, do them on yourself. Now that you know the process to them, do them in your own little free time. If you have a paper in front of you, do them real quick. I'll pause for a minute before I move on. Alrighty, welcome back. Now we're going to be moving on to chapter 2.4, section 2.4. So this is all about atomic weights. So atomic weights, just a quick little synopsis of where they are. If you look on your periodic table, you'll have your atomic number, symbol, element name, and then you're also going to have a number at the bottom. The fun thing about atomic weights is they are not exactly the same as what we just did, since there are multiple different isotopes of one atom. So, yes, in theory, carbon should come out to 12. There are many different isotopes of carbon that you have to take account of. which make it come out to actually 12.01. The way we do this is, so atomic weights, we do sum of all, so this could mean basically all the different isotopes that there are. For example, right down here, we're going to be using 2 different carbon isotopes. So that means that we have to do, and we're going to use carbon as our example, we have 2 isotopes of carbon. One is carbon 12, one is carbon 13. So carbon 12 makes up 98.93% of all carbon. So before I go anywhere else from here, we can kind of assume that the atomic weight of carbon is going to be close to 12. It's not going to be super deviated because almost all of carbon you're ever going to find is going to be carbon 12. Next, we take all these things, plug them into this equation down here. So follow this formula all the way down. So, all right, we have carbon 12, 12 AMU, which is your mass, and then you have your percent abundance, which is going to be 98.93. Do this, and then same thing for carbon 13. 13 point, well, there's a little fun thing added on there, but unnecessary for right now. But 13, and then your percent abundance. So then, for how many isotopes you have, you continue this on until you have included all your isotopes, and then bada bing, bada boom, you got your number. That's going to be the number that is the average atomic weight for carbon. So let's do this problem first. Right here. So do it real quick on a piece of paper. If you need to pause the video, and I'll show an answer in a minute. Alrighty, welcome back. There's going to be your answer for you. So since there is more, well, we're working with boron here. So since boron is 10.8, that means that it's closer to boron 11. So it's going to be, that's going to be the more prevalent isotope. So there's going to be a higher quantity of boron 11 than the boron 10. Next exercise. So the next thing we're going to be doing is this. What I want you to do is do this problem on a piece of paper and then come back. Alrighty, welcome back. Here's going to be your solution. So you take your things right here as you get from the problem. So chlorine 35. So it's using a little bit of rounded number and unrounded numbers here. So if you used if you use the numbers up here, you're all good. We're going to slightly answer deviating from this. If you use this number, even better. So again, we're going to do the plug and play type thing. Percent right here, atomic mass right here. Since we have 2 isotopes, we make a second one. Same thing. Run it through a calculator. Bada bing, bada boom. There you go. Hopefully this helped you, and good luck on your AP test.